Ladies and gentlemen, I'm glad that you're here. My name is Piotr Bazydło, and I'm a leader of Network Security Methods team at Research and Academic Computer Network NASK. And today I would like to tell you something about our Darknet, what this Darknet really is, what can we see in there, what can we find in there, and how can we use this data for the practical stuff, so operational actions, intelligence-driven actions, and so on. So to begin with, I hope that you've read an abstract, because I'm not going to talk about Darknet like deep web, so the black markets, drug selling stores, and so on, but I'm talking about raw network stuff. So in our case, Darknet is just an unused space of IP addresses. These are not used IP addresses, and it's often called as a network telescope. So to begin with some introduction, we can divide, for example, the internet for the two spaces. Active IP space, so the space where we've got IP addresses that are indexed, we've got some DNS for these addresses. We, for example, have some websites, services, applications going on their users, etc., etc. And then, on the other hand, we've got this Darknet IP space. So these IP addresses are not registered anywhere. We've got no DNS records, no services going on there, no users, and so on. And typically, we should observe no traffic in here, because these IP addresses are not used. But in practice, it occurs that we've got actually quite a lot of network traffic in there, and this traffic can be right away marked as suspicious, because it should not be really there. And in the beginning, I would like to tell you what are the sources of these packets, and then during my presentation, I would like to show you some use cases, what we are doing with this traffic, what can we learn from it, how are we fingerprinting different botnets, and so on. So in the beginning, the first main source of packets seen in Darknet is the misconfiguration of network devices and applications. So it's very simple. For example, somebody is sending a packet for someone who is configuring its software or something like that. He made a typo, and he sent us the packet which was destined for somebody else. I know that I've used local IP addresses in here, but I'm actually quite scared of GDPR right now, so just to be sure that nobody is going to shout at me, I've used local IP addresses. The second thing that we see in Darknet is a scanning activity. So, for instance, we can get, for example, some infected hosts that are scanning through the internet. They are looking for some open ports from some services or vulnerable devices or applications. And if they are generating IP destination randomly, it's only a matter of time, because sooner or later, these packets will hit our Darknet IP space, and then we are going to see these packets. The next thing, probably one of the most interesting one, is backscatter from denial of service attacks. So if we've got, for example, a bot master who is ordering his bots to perform a spoofed attack, they are, for example, randomly generating IP source addresses because they are spoofing this attack. If they have used our Darknet address, then we are getting responses from this attack. For example, if somebody is sending a SYN packet, we are getting SYN ACK response, or for example, in case of ACK floods, we've got, for example, RST responses. And then we can analyze this traffic and detect victims of denial of service attacks. Then we've got exploitation attempts. So we are sinkholing whole traffic. So it's not a honeypot. We are not providing any responses. We are just sinkholing the traffic. So we've got no TCP connections in there. However, we can still observe quite a lot of malicious UDP packets, because sometimes malicious actors just are sending UDP packets with payloads, so they are at the same time scanning the internet and performing exploitation activities at the same time. And in the end, we've got weird and undefined stuff, because we've got quite a lot really weird packets. Usually, I believe we are looking at script kiddies right there, but sometimes possibly there are some smart guys that are knowing what they are doing, but we are just not smart enough to figure it out. Okay, so it looks quite easy, I believe, at the beginning, because, for example, we've got this NASK packet, we can say that we are looking at denial of service victim and so on, but it occurs that it's not so simple, because if you look at some basic numbers, we've got more than 100,000 of these IP addresses. So we are getting about 25 billion of packets per month, and it gives us about 800 million of packets per day, and more than 500,000 of packets per minute. So we've got quite a lot of traffic to investigate, to look through. So it's quite a lot of work to do. And what are the main problems when we are looking at this traffic? So first of all, we've got to group it. We've got to analyze it and classify it into events. For example, this and this botnet performing a scanning activity for this and this port, or for example, synflat victim or something like that. And we are trying to define which event is interesting or not, and we are trying to fingerprint responsible actors. So, what can we do with this traffic? So first of all, we can detect and analyze denials of service attacks. Then we can fingerprint actors and botnets responsible for this attack. I will talk about it later, and I will show you how we can do that. We can observe massive scan campaigns and observe responsible actors. We can track botnets, we can track their actions. We can forecast exploitation campaigns and even zero-day exploits, and it's pretty interesting part in here. And we can detect new network signatures. It's the packet generation algorithm PGA, but I'm going to talk about it in the second part of our presentation. I can show you some examples for this. And other actions related to that stuff. In here, we've got one slide with some basic statistics from where we are getting most of the packets in the darknet. So we've got the data from April in here. As you can see, that top countries that are sending us packets are China, USA, Russia. We've got Brazil, Netherlands, UK, Poland, and France. I believe these are the top countries that we are seeing the packets from. And right now, I would like to go straight to some use case. In here, we've got a timeline. And on the time, I believe it starts on the, oh, sorry, somebody went wrong. Okay, so we've got a timeline. It starts on the 9th of February and lasts for 5 days. And in here we can see TCP scans destined for port 8080. And as you can see at this chart, we can see that we've got a constant level of these scans going on. We've got about 10,000 scans per 5 minutes because we are sampling here per 5 minutes. And then suddenly we can see an uptick in the traffic. So the amount of scans has increased dramatically. About 25,000 number of additional scans per 5 minutes. And if we are going to investigate through this traffic, it occurs that the packets which has provided us the uptick have the following signature. The sequence number is equal to IP destination. And I believe some of you may already know that this is a signature of a Mirai botnet and other botnets that use the Mirai code, because Mirai code leaked out some time ago, and many different IoT or Android IoT botnets or Android worms are using this code right now. So if we are going to investigate further and filter out this traffic, we've got another timeline with only scanning activity for this port, but only with this signature. And it actually looks quite perfect, because we can see that there was exactly nothing happening before. And now we've got this sudden uptick, and we can see that some botnet, maybe some actor, is performing some scanning activity. Probably he is trying to exploit something. So, as I said before, Darknet has its limitations. So we are not responding to these packets. We've got no honeypots in there. So we are not seeing the exploitation itself. So right now we are not really sure with what we are dealing with. But we can, for example, use one of the most powerful InfoSec tools, so the Twitter. And we can see that Quiho 360 NetApp has provided an alert that the new variant of Satori botnet is trying to exploit JSON routers. So they were right here. What we have seen in here is just Satori botnet using a new vector to spread through the vulnerable devices. And the timeline matches perfectly. So we've got it detected pretty well. And right now I would like you to look at this downtick in the activity because I'm going to talk about it really soon. So right now, what can we do with it? Of course, we can fingerprint. We can find infected devices, we can collect IP addresses, provide feedbacks to certs and other responsible parties for managing incidents and so on. And in here, during these 4 or 5 days, we have fingerprinted about 35,000 of unique IP addresses of this botnet. However, of course, we've got dynamic IPs, DHCP stuff, and so on and so on. So we were trying to estimate, and we have figured out that there were about 35,000 of devices infected. All right, but we can see also that the Asia has a lot of data center routers because mainly we've got Vietnam, China, Korea, Thailand, Japan, and so on. And now let's go back to this downtick in the scanning activity, in the scanning traffic, because as you can see in here, we've got this downtick visible. It's not so visible if we are not looking just on these packets with the signature. However, it often occurs that if one event ends, another event starts, because these botnets, for example, do not like to be idle. So, for example, if they have finished to exploit one vulnerability, they are instantly starting to exploit something else. And as we can see, in here the green line is, I believe, for the port 81. So it occurred that the Satori botnet has decreased its activity for the data center routers. Maybe they said, okay, we've got enough, and now we are starting to exploit some IP cameras, and also Huawei routers, because in here we've got port 52,869. So we can, if we have once detected the botnet, we've got IP addresses and we are monitoring in actions, we can look at another stuff that this botnet is performing, because it really looks just like that. They've stopped to do something and they have started to do something new at the same time. So we can look at something like that. And right now I would like to talk a little bit about forecasting, because right now I have provided you a simple example how we can, for example, track this botnet, how we can fingerprint, find IOCs and so other stuff. But one of the most interesting things about Darknet is that we can just forecast that something is going to happen very, very soon. Let us imagine a simple scenario when we have, for example, some very high port that is not really used, and we've got like 5 or 10 UDP or TCP scans for this port per day, because somebody was performing some whether vertical scanning activity, or maybe they were just scanning random ports and so on. And then we've got like 500,000 of scanning packets during 1 hour for this port. So it means that, for example, somebody has found some vulnerability, or maybe they are going to exploit something or use it for some malicious actions. And now let's talk about memcached. I believe that all of you have heard about memcached, about that there were 2 major events connected with memcached. The first event was a GitHub denial of service attack. So it was a new record for denial of service attack. It was 1.3 terabits per second. And another event was another denial of service attack reported by Arbon Networks, and it reached about 1.7 terabits per second. And as I was talking earlier about this, that we have these ports that are not really scanned and so on and so on. So the exact same thing was about memcached. So memcached was not really scanned in our Darknet. We have seen almost no traffic for it. And now let's look at the scanning activity on this timeline. And as you can see, we've got 2 scans per day, 4 scans per day, 1 scan per day, and now we've got 20th of February, and suddenly about 500,000 of scans for a memcached. Okay, so it's getting quite suspicious. Then again, we've got some small break, and again, another scanning activity, it has grown up a little bit. Then we've got a GitHub attack, and the scanning activity is growing up because it was a very loud attack. A lot of different actors and parties got very encouraged by it. They started to exploit it, started to look for something, and so on. So just looking at this time period, we can say that we can really dig into the case, and we can even maybe not find out, but it may help us to find out who was really responsible for the GitHub attack. So I'm going to provide some short information, because I believe about this memcache stuff we could just do the separate presentation. But let's look at the first day. We've got only 3 IP addresses that were performing this scanning activity, and all of these were located in the United Kingdom. All 3 IP addresses were located within the same host and autonomous system number from DigitalOcean. Whole scan lasted only about 25 minutes. 2 different source ports were only used during it, and all the scans had the same payload. So as we can see, we've got 3 IP addresses located at the same place, and we have only 1 payload, so we've got a scanning pattern. Another 4th day after the break, we've got 2 IPs scanning for the memcached. The first one is the IP address from United Kingdom, and it's the same one that we have seen 2 days earlier. However, we've got a new IP address. It's from Singapore. But it occurs that still the same ports are used. The scanning activity lasted for about 25 or 30 minutes, so it's the same time. And we still have the same payload. So the identical payload was used, and it was pretty weird because it was a common memcached payload, however with some additional bytes which were unique. So we believe that we are still looking at the same actor that is performing this activity. However, another day, we've got 1 scanning IP address from the USA, and the scan seems totally different because the source ports were randomized, new payload has been used, and the scan lasted for about 3 hours. So maybe they have changed tactics, but there is a very big possibility that another party, another group got maybe some feedback about the memcached, have figured out that memcache can be used for something like that, and they have decided to scan too. So I'm not going to dig through each of the day because we have not a time for this, but I will just like to show you simple statistics before the GitHub attack and after the GitHub attack. So before the GitHub attack, we've got only 60 IP addresses that were scanning the internet looking for vulnerable memcached machines. Most of these were located in the United States, and we have detected 4 or 5 scanning patterns. So at most, we've got 4 or 5 groups that were scanning the memcache before the GitHub attack. So we've got 4 or 5 parties that could perform this scanning, GitHub attack. However, it's possible that there are less actors, but they have changed some tactics. On the other hand, we've got another 7 days after the GitHub attack, and we can see that we've got more than 300 IP addresses with multiple different scanning patterns, so it's getting fuzzy right now. And we've got a lot of IP addresses from United States. However, China came into play, and China started to exploit memcached a lot too. And between these 2 big attacks, there were a lot of memcached attacks going on. So they were exploited for the whole time until ISPs has started to filter out the memcache traffic. And as I've been saying about these scanning patterns, we can define these patterns, we can define some actors. In case of memcached, we are, for example, looking at unique payloads or very similar payloads but with only slight changes. We were looking at source ports, how they were generated. We were looking at pairs of characteristics. For example, we were connecting how the source ports were selected, what was the payload, how long the scanning activity was lasting, and so on. And just to finish the case of the memcached, I can show you 2 short cases for the source port, because I think it's really useful and interesting to look into source ports, and not only in Darknet, but when you are, for example, mitigating denial of service attacks, if you are analyzing honeypot or sandbox traffic, just basically everywhere. And people often forget to do that as I'm talking with them, because as you can see, in here we've got top 5 source ports that were used during these memcached scans, And what we can see that we've got one particular port that is used more frequently than another. And it's pretty funny because it's just a reverse memcache port. Yeah? So the one number 1 is exchanged with number 2, and we've got reverse memcache port. And in here we've got also an interesting case, in not typical case, because the same source port was used as the memcache destination port for scanning. So the signature was that the source port was equal to destination port. And if we look at these cases, it occurs that in the first example, we've got only one IP from France that was performing this scanning activity. So we can right away just fingerprint, okay, we've got an actor that is using a memcache with this source port. Probably, I'm not sure, but probably if you would look into some attacks, it may occur that they've also used the same source port during the attack. So when we can, for example, connect the actors that were using the same tools. And the second case is, I believe, more interesting, because in the case when we've got the source port equal to destination port, we've got 56 IPs from United States that were performing this activity, and the scan was pretty well organized. So because they have used a lot of different IPs located within the same ASN for the scanning activity, they've used the same payload, so we are definitely looking at the same actor right there. But at one shot, looking only at the source port, we have fingerprinted one actor, and from these 300 IP addresses, we can just take away more than 50, and we have probably the same guy in there. And okay, I promised that I will show something connected with denial of service attacks. So in here we've got a very short and simple example, but I think quite interesting somehow. I believe that you have heard about the Telegram ban in Russia. So after this ban, some folks did not have to wait for a long time, and they have decided to perform a flooding activity for this Telegram, and they have managed to dose it. And if we look at the Darknet, whether we have some hits for this, whether we have seen a backscatter from this attack, it occurred that yes, we have seen ACK packets coming from this Russian watchdog. And as you can see, it was for port 443, so for HTTPS. The whole denial of service lasted for about 25 minutes. It was SYN-FLAT, by the way, because we've received a lot of SYN ACK packets. But it's not the most interesting part about this attack. It has occurred probably, we are not 100% sure, but I've been talking about with some guys which are performing some DOS mitigation actions. And during this attack, we have started to receive ACK packets from this Russian watchdog. So probably we are looking at some mitigation actions that Russians are performing, because, for example, I don't know, they would like to check whether the half-open session will be used. Should they sustain the sessions, or should they just deny it and forget about it? So I believe that we are looking at some mitigation actions from them right now. So it's often very possible just to look at the denial of service attacks and see the mitigation actions that are performed. But it's not all. If we are talking about this Russian watchdog, another attack was performed 3 days later, and it was also quite interesting because we've got this SYN-FLAT activity and we've also seen the mitigation actions. However, we have also received ICMP packets from there. And actually, we love these ICMP packets, because if we are going to talk about backscatter, we only are getting responses from the victims. So it's not very, okay, it's accurate, but we are losing some information. However, if we are receiving, for example, ICMP packets when, for example, we've got a message that destination is unreachable, port unreachable, or TTL is expired, we can see the actual original packet that was spoofed and used for the attack. So in here, what was the really interesting fact, that it has occurred that this Russian watchdog was not only SYN-flooded, but it was also ACK flooded, because we've received a lot of ACK packets, and destination port during this attack was equal to 0. They probably were trying to attack firewall or bandwidth. And the sequence, the third and fourth byte of sequence number and acknowledgement number was equal to 0. And it's somehow something that we call a PGA signature that we can use to track different tools, botnets, which were performing scanning, exploitation, or attacks. And right now, from this case, I would like to go to the PGA case. So what this PGA stuff is that I'm talking about? It was firstly mentioned by the 316 NetLab keyhole, 316 NetLab, during botconf, I believe. And it occurs that different tools and malware often utilize different packet generation schemes, packet generation algorithms in order to simplify or fasten their packet generation procedure. And usually they are using such as signatures during scanning or during denial of service attack. These are usually based on some simple operations. For example, they are randomizing 2 bytes and then they are, for example, copying this byte into another byte, or they are incrementing it, they are swapping, perform XOR operation and something like that. And during the project, we have developed automatic tool for detection of such a signatures. So we are constantly monitoring Darknet traffic, we are looking for new signatures, and we are tracking these signatures. But of course, if we have found out some signatures in the Darknet traffic, we are unable to map it to some party tool or malware. However, we are also trying to sandbox the malware, and if we have got traffic from sandboxes, we are PGA-ing it, and then we can say, okay, PGA has detected in the sandbox traffic this and this signature. We can mark it as, for example, Satori botnet, and then we are looking at the Darknet traffic, and we are looking for IPs that are infected with this botnet, and then we are trying to fingerprint and track their actions. And just to have some example for the PGA, how for example, it may look like, in here we've got 20 packets, a DNS flat. And as you can see, the IP ID is the same as the DNS ID. So the first byte of IP ID is equal to the first byte of DNS ID, and the second byte is equal to the second byte. However, you can also look at the IP source, because source IPs were spoofed in there. And as you can see, the second byte of IP ID is equal to the third byte of IP source, and the first byte of IP ID is incremented by 1 and then it's equal to the last byte of IP source. So it's just an example of signatures. We've got quite a lot of them, and as you can see, we can fingerprint a lot of different actors performing the malicious activity. But why do they even bother? I believe it's hard to tell, because somebody can say, okay, it's easy to fingerprint them or to mitigate denial of service attacks because of this signature. But I believe they know the risks, and what they are trying to do, they are just going to fasten the attack. I've made a small experiment. I've written a very simple Python code using Scapy, and I have implemented 2 different PGAs. The first one, the legitimate, when the IP ID, source port, and the sequence number were totally random. And then I've taken the signatures from the DRDoS botnet, so the biggest botnet responsible for SYN flats right now. The signature looks like this. The IP ID is equal to source port, and the first 2 bytes of sequence number are equal to this IP ID and source port. And after this experiment, when I have generated 1 million packets for each PGA, it has occurred that we've got 24 more packets per second. It's not a lot of, but if we assume that the botnet has 100,000 of infected machines, it occurs that we've got about 2.5 million more packets per second. So it's quite a more effective approach, and I believe that's why they are just using these signatures. So, for example, we've got Mirai. Sequence number is equal to destination IP, and it's definitely faster, but not only, because they do not have to store information about targets that they were scanning, and they do not have to wait for the response. They're just sending this packet. Then, when they received a SYN ACK packet, they check whether the acknowledgement number can be connected with the IP from which they got the IP address, and then they say, okay, it's a hit, we've got a machine with an open telnet or any other port that Mirai is scanning the activity. And then again, about the XOR DDoS, because I've shown its signature. And if we look at the denial of service attacks, is it really easy to detect this botnet? If we are talking about XOR DDoS, it's not so obvious, because when we are receiving SYN ACK packets, we are only seeing the backscatter, and we lose information about IP ID, and the IP ID is used by this botnet during its operation during the SYN floods. So we can only compare destination port and acknowledgement number in the packets that we have received. However, as I've been saying it earlier, we love ICMP packets because we've got original packets that were performed during the that were generated during the attack. It sometimes occurs that, for example, during a flood, we've got about 50,000 SYN ACK packets, and we have received 1 or 2 ICMP packets because TTL expired, or because of, I don't know, something was wrong with routing, or for example, destination port was unavailable for a while because, for example, DDoS was successful. And then we can see the original packet with the IP ID as it was originally generated. So then we can see that, okay, in the SYN ACK, we've got this part of signature that was okay, and then we also got this packet, this payload from the ICMP with original packet. We are looking at the IP. Okay, signature matches in here too. So we are definitely looking at the XOR DDoS performing the attack. And these signatures are everywhere, really. If you would look, if you are, for example, mitigating the denial of service attacks or something like that, just look at the headers, and I believe that you will see plenty of that stuff. In here, we've got an example attack detected in our Darknet on one destined for one of IPs belonging to Google. And the attack was split into 2 parts. During the first part, we've got such an PGA signature in here. So the destination port was equal to the first byte of acknowledgement number. And in the second part of the attack, we've got the signatures when acknowledgement number, third and fourth byte were hard-coded with 0 values. And destination port was equal to third and fourth byte of IP destination. So what can we tell about it? First of all, definitely during 2 phases of attack, 2 different tools were used for the attack. Maybe it was different botnet, different tool, I don't know. But definitely we are looking at 2 different tools because we've got 2 different signatures. And if you would look at this from the point of the attacker, how they are generating their packets, in the first part, we've got a source port equal to the first 2 bytes of sequence number. So it's matching with the XOR DDoS botnet, for example. In here, we've got hard-coded third and fourth byte of sequence number to FF values. And in here, for the end, we've got source port equal to the third and fourth byte of IP source. Okay, so I believe I've told you everything that I wanted. I believe I still have some time. I was too fast. What can I say about Darknet? Darknet is really great. We can see a lot of different stuff in there. As you have seen, we can fingerprint a lot of malicious actors. We can predict some stuff because before the memcache attack, if we would look at this, we could say, okay, something is really going to happen with this memcache stuff. But it has its limitation. We've got no TCP connections in there. We are not responding to packets. So the best thing is to connect Darknet with other sources like honeypots, sandboxes, and any other similar stuff. So we are trying to correlate our Darknet data with honeypots and sandboxes because we are sandboxing malware. We can then, for example, see on sandboxes that this and this malware is performing such activity with this and this signature. Then we are just taking the signature and we are tracking this botnet in the Darknet. So we can find a lot of infected devices, and we can just look at the change of their tactics, so they are performing new in there. We are open for any collaboration connected with the PGA stuff, so if you, for example, have some weird traffic, would like to fingerprint it, we can use our tool, we can just collaborate on the stuff because we are very interested in mapping these signatures found by us to the different tools and malware. And for the end, we've got in here other people involved in this work. So we've got Adrian Korczak and Mateusz Goniprowski, my teammates from NASK. They were responsible for some development actions. We've got Krzysztof Lasota and Paweł Pawliński from CERT as consultants. And of course, we've got 360 NetLab because they have invented the PGA stuff. I'm collaborating with them about this stuff. and for the intelligence, because they are providing us some network traffic, and they are providing intelligence via Twitter and something like that. So once again, thank you for your attention. I hope that you like the presentation. I hope that you've seen that we can use the Darknet for quite a lot of stuff. You can check out my Twitter. I've not been writing a lot recently because I have not the time, but I'm going to catch up during June and work on some interesting cases in Darknet. You can see the Sysden blog because I'm trying to write some blog posts about fingerprinting in there. And once again, thank you. If you've got any questions, I'm open for a discussion.